Cognitive radio network paradigms. Since its introduction the definition of cognitive radio has evolved over the years. Consequently, different interpretations of cognitive radio and different visions for its future exist today. In this section we describe a few communication models that have been proposed for cognitive radio. We broadly classify them into overlayer known interference models, underlayer interference avoidance models. The underlay paradigm encompasses techniques that allow communication by the cognitive radio assuming it has knowledge of the interference caused by its transmitter to the receivers of all non-cognitive users. In this setting the cognitive radio is often called a secondary user which cannot significantly interfere with the communication of existing, typically licensed, users, who are referred to as primary users. Specifically, the underlay paradigm mandates that concurrent non-cognitive and cognitive transmissions may occur only if the interference generated by the cognitive devices at the non-cognitive receivers is below some acceptable threshold. The interference constraint for the non-cognitive users may be met by using multiple antennas to guide the cognitive signals away from the non-cognitive receivers, or by using a wide bandwidth over which the cognitive signal can be spread below the noise floor, then to spread at the cognitive receiver. The latter technique is the basis of both spread spectrum and ultra-wideband (UWB) communications. The interference caused by a cognitive transmitter to a non-cognitive receiver can be approximated via reciprocity if the cognitive transmitter can overhear a transmission from the cognitive receiver's location. Alternatively, the cognitive transmitter can be very conservative in its output power to ensure that its signal remains below the prescribed interference threshold. In this case, since the interference constraints in underlay systems are typically quite restrictive, this limits the cognitive users to short-range communications. While the underlay paradigm is most common in the licensed spectrum, for example UWB underlays many licensed spectral bands, it can also be used in unlicensed bands to provide different classes of service to different users. The enabling premise for overlay systems is that the cognitive transmitter has knowledge of the non-cognitive user's code courses and its messages as well. The code course information could be obtained, for example, if the non-cognitive users follow a uniform standard for communication based on a publicized code course. Alternatively, they could broadcast their code courses periodically. A non-cognitive user message might be obtained by decoding the message at the cognitive receiver. However, the overlay model assumes the non-cognitive message is known at the cognitive transmitter when the non-cognitive user begins its transmission. While this is impractical for an initial transmission, the assumption holds for a message retransmission where the cognitive user hears the first transmission and decodes it, while the intended receiver cannot decode the initial transmission due to fading or interference. Alternatively, the non-cognitive user may send its message to the cognitive user, assumed to be close by, prior to its transmission. Knowledge of a non-cognitive user's message and/or code course can be exploited in a variety of ways to either cancel or mitigate the interference seen at the cognitive and non-cognitive receivers. On the one hand, this information can be used to completely cancel the interference due to the non-cognitive signals at the cognitive receiver by sophisticated techniques like dirty paper coding. On the other hand, the cognitive users can utilize this knowledge and assign part of their power for their own communication and the remainder of the power to assist, relay, the non-cognitive transmissions. By careful choice of the power split, the increase in the non-cognitive user's signal-to-noise power ratio, SNR, due to the assistance from cognitive relaying can be exactly offset by the decrease in the non-cognitive user's SNR due to the interference caused by the remainder of the cognitive user's transmit power used for its own communication. This guarantees that the non-cognitive user's rate remains unchanged while the cognitive user allocates part of its power for its own transmissions. Note that the overlay paradigm can be applied to either licensed or unlicensed band communications. In licensed bands, cognitive users would be allowed to share the band with the licensed users since they would not interfere with, and might even improve, their communications. In unlicensed bands cognitive users would enable a higher spectral efficiency by exploiting message and code course knowledge to reduce interference. The Interweave paradigm is based on the idea of opportunistic communication, and was the original motivation for cognitive radio. The idea came about after studies conducted by the FCC and industry showed that a major part of the spectrum is not utilized most of the time. In other words, there exist temporary spacetime frequency voids, referred to as spectrum holes, that are not in constant use in both the licensed and unlicensed bands. These gaps change with time and geographic location, and can be exploited by cognitive users for their communication. Thus, the utilization of spectrum is improved by opportunistic frequency reuse over the spectrum holes. The interweave technique requires knowledge of the activity information of the non-cognitive, licensed or unlicensed, users in the spectrum. One could also consider that all the users in a given band are cognitive, but existing users become primary users, and new users become secondary users that cannot interfere with communications already taking place between existing users. To summarize, an interweave cognitive radio is an intelligent wireless communication system that periodically monitors the radio spectrum, intelligently detects occupancy in the different parts of the spectrum and then opportunistically communicates over spectrum holes with minimal interference to the active users. For a fascinating motivation and discussion of the signal processing challenges faced in interweave cognitive radio, we refer the reader to Table 1 summarizes the differences between the underlay, overlay and interweave cognitive radio approaches. While underlay and overlay techniques permit concurrent cognitive and non-cognitive communication, avoiding simultaneous transmissions with non-cognitive or existing users is the main goal in the interweave technique. We also point out that the cognitive radio approaches require different amounts of side information. Underlay systems require knowledge of the interference caused by the cognitive transmitter to the non-cognitive receivers. Interweave systems require considerable side information about the non-cognitive or existing user activity, which can be obtained from robust primary user sensing, and overlay systems require a large amount of side information, non-causal knowledge of the non-cognitive user's code course and possibly its message. Apart from device-level power limits, the cognitive users transmit power in the underlay and interweave approaches is decided by the interference constraint and range of sensing, respectively. While underlay, overlay and interweave are three distinct approaches to cognitive radio, hybrid schemes can also be constructed that combine the advantages of different approaches. For example, the overlay and interweave approaches are combined in. Before launching into capacity results for these three cognitive radio networks, we will first review capacity results for the interference channel. Since cognitive radio networks are based on the notion of minimal interference, the interference channel provides a fundamental building block to the capacity as well as encoding and decoding strategies for these networks. Comparison of underlay, overlay and interweave cognitive radio techniques.